Hello, my name is Niall Maguire. I am a fourth year PhD student at the University of Strathclyde in Glasgow, and today I'll be walking you through our ECIR 2026 paper titled Cross-Sensory Brain Passage Retrieval, Scaling Beyond Visual to Audio, which was co-authored by my supervisor, Dr. Yashar Mushvegi. So one of the fundamental challenges that remains in information retrieval presently is the ability of users to communicate their internal information needs to what we define as comprised query states, these being the actual textual query representations that you would submit to any sort of text-based retrieval system. And there's a couple of reasons and hypotheses as to why this is problematic. Firstly is the cognitive resources that are immediately required to enable this process. As these cognitive resources are used up potentially by other tasks or during this task, it becomes more and more challenging for you to actually communicate what you want to search for. Similarly, you also have the semantic gap issue where as your information need moves from almost a sort of a visceral feeling to the comprised query state, you lose some of the semantic richness and intention of what you're actually wanting to search for, meaning that the final query representation that you produce may not accurately reflect what you actually want to search for. And lastly, you also have ill-defined information needs, and this is where you have a searcher trying to formulate an information need for a topic they don't have enough information about to actually formulate an accurate query. So it almost becomes semi-paradoxical. You know, how could you expect somebody to formulate a query for something they don't actually know anything about? And so this is what we call in information retrieval the information need to query formulation gap. On top of this, you also have additional factors that compound these issues. Some examples might include if you're dealing with searchers that have physical constraints and have physical disabilities and are unable to express their information needs through traditional means, i.e. Typing into an actual computer or vocalizing their information need. But then you also have things such as environmental constraints. You know, if you're preoccupied with a task such as driving your car or riding a bike, all of this combined further constrains the ability of searchers to communicate their information needs effectively. So what are the potential solutions to this? Well, in the past 10 years within information retrieval, there's been a growing avenue of applying neuroscientific and neuroimaging methods to study the physical manifestations of information retrieval concepts. Some concepts might include things such as relevance, information need realization, and information need satisfaction, just to name a few. And so my research focuses on the application of these neuroscientific approaches and neuroimaging methods to help alleviate the query formulation challenge. One such paper that we did on this topic, we presented at ECIR 2025 last year in Padova, titled Brain Passage Retrieval. And what this did was it enabled the semantic extraction of information while participants were visually processing text, and then using the EEG that was captured during those trials as an actual query representation to then pull back relevant textual passages without the searcher ever having to express an information need. Now, as you can probably guess from the title of the paper, one of the major constraints and one of the areas we wanted to look into beyond our previous ECIR paper was that currently it has no capability of processing or understanding auditory-based stimulus from EEG, which is problematic as obviously audio evoked stimulus is present throughout our day-to-day lives. I'm presenting these slides through an audio channel, but more concretely within an IR space, you have quite an integration and push for audio-based conversational search. Some prime examples include conversational assistants such as Siri and Alexa, and more recently ChatGPT's voice mode. But then on top of that, you also have a huge quantity of information and documents encoded within audio, things such as audiobooks, podcasts, and even music as well. And lastly, EEG data is already a very expensive and time-consuming data modality to collect, and there's not a huge amount that's publicly available. So if you could train across both visual stimulus and auditory stimulus to improve downstream retrieval performance, this would greatly expand the availability of data to train on and potentially improve overall retrieval performance for these systems in the future. And so to concretely define some of our research questions, firstly we wanted to examine can auditory EEG signals serve as effective brain passage retrieval queries, and how do they compare to visual EEG queries? Does combined auditory visual training improve retrieval performance? And lastly, how does combined auditory visual training compare to its text query counterpart? So for this, we also needed two datasets, one in audio and one in visual. For the audio dataset, we used the ALICE dataset, which was collected from 49 unique participants, where they were passively listening to the first chapter of the Alice in Wonderland's audiobook recording. And this was recorded using a 61-channel EEG headset, sampled at 500 Hz. And then for the visual dataset, we're using the Nieuwland dataset, which uses 80 original sentences that were bespokely written for that dataset, where each word appears on screen, one word at a time, for 500 milliseconds. And this was collected from 51 unique participants, also using a 64-channel electrode EEG headset, also sampled at 500 Hz. And the main justifications as to why we picked these two datasets in specific was obviously you can see that they're quite evenly matched in terms of number of unique participants, but more importantly, they are as closely matched as possible in the number of electrodes and sampling rate, which means that we are capturing roughly the same spatial regions and activations within the brain. Now, one of the limitations of these datasets is that they don't come out the box with query document pairs, which is obviously a necessity to train any sort of neural ranker or retrieval model. And so to do so, we leverage the inverse close task, which if you imagine you have a given text segment that the participant would have read or listened to, and the corresponding EEG recorded while they are reading or listening to that piece of text, we extract a given span. In this case, for our training scenarios, 30% of the overall sentence length is extracted, and the EEG from that segment is used as our positive query in this case. And then the remaining text within that sentence is used as our positive document with respect to that query, where 90% of the time the query terms are then masked from the textual passage setup, meaning that we can then actually train a neural retrieval model on this data. So just quickly going over the model architecture, builds on top of the traditional bi-encoder setup, where you have a query encoder and a passage encoder. In this case, we're swapping out the traditional text query encoder with an EEG query encoder. And then for the text passage encoder, we're using a frozen BERT uncased model, which remains frozen throughout training, and the only thing it does train is our brain query encoder. And then for the actual training objective, again, just using your traditional info NCE contrastive objective, where it's the model's objective to match positive queries to their corresponding positive textual documents, and then push away within the embedding space any documents and text that aren't relevant to our EEG query. So firstly, for the evaluation, we wanted to address each of the three research questions we had. And for this, for research question 1, we trained two models. One trained solely on auditory datasets and evaluated on auditory datasets, and then one trained solely on visual datasets and evaluated solely on the visual dataset, where we then have a lower bound in performance, which is the random EEG noise, which is random noise sampled from the distribution of the EEG test set, and this kind of serves to show and demonstrate that our models are actually learning of something of semantic value, rather than just learning some spurious features within the EEG data. For research question 2, exact same setup as before, except this time we train one more model, which is pulled across both audio and visual datasets, but then evaluated on their respective datasets. So this is to sort of look at, does pulling across both sensory modalities help to improve the respective downstream performance for each of their modalities? And then lastly, for research question 3, how does the combined auditory visual training compare to its text query counterparts? For this, we just have two retrieval models that process the actual textual queries instead of the EEG queries. In this case, we have one lexical model, i.e. BM25, and then one neural model, which is Colbert V2. And then for the metrics we report mean reciprocal rank, MRR, and hit at K, where K is equal to 1 and 10 in this case. So firstly, can auditory EEG signals serve as effective BPR queries, and how do they compare to their visual EEG? So we have each of the metrics on screen, as you can see, where we have random noise, auditory EEG and visual EEG models for each. And straight away, as you can see, the auditory EEG and visual EEG substantially outperform random noise, which is encouraging to see, meaning that they're learning something of actual semantic value. But then the key takeaway here is that we see a massive improvement from the auditory EEG over the visual EEG queries, which is really interesting to see, as we had no experience with auditory EEG before. So that helps to address, firstly, research question 1. Okay, so for research question 2, does combined auditory visual training improve retrieval performance? This is where we pull across both training datasets for a single model and evaluate it on the respective datasets, where the new bar here, which are the full bars, are the combined training scenarios for both audio and visual. And as you can see, compared to their individual training counterparts, yes, they substantially improve performance, which was excellent to see, showcasing that yes, pulling across sensory modalities for EEG stimulus does help to improve retrieval performance. Also interesting to note is that as you pull across both training setups, you do begin to see visual performance begin to catch up to that audio performance. So we're not seeing as much of a gap between the two, which is very interesting to see. And then lastly, for research question 3, how does combined auditory visual training compare to its text query counterparts? And again, here we have our audio and visual combined trained models compared against BM25 and Colbert V2, when instead of given the EEG queries, they're given the actual textual queries. And what's really exciting to see here is that for the first time, we're seeing for MRR and HIT at 10 that the auditory EEG model actually outperforms Colbert V2 and BM25 when they're processing the text queries, which was very exciting to see. Now, for all the other metrics and the visual EEG, while they don't outright outperform both BM25 and Colbert V2, they begin to close the gap substantially, which was very encouraging to see. So, in conclusion, we firstly established that auditory simulated EEG queries can be used as query representations. Cross-sensory training does help to improve overall retrieval performance and helps to mitigate the data scarcity of open source EEG datasets. And lastly, cross-sensory training helps to close the gap between EEG and text query representations. So on screen we have the QR codes for the GitHub repository for this paper. We also have the QR code that takes you directly to the paper itself. We have our NeuraSearch social medias if you're interested in following us on Twitter and LinkedIn, and then we also have our own personal Twitters and LinkedIn codes up there if you're interested. Thank you for watching.